maybe students think that dative bond is special because of teachers like me who keep a unique, just a whole lesson for dative bond. तो students को लगता है कि ये कोई बहुत different चीज़ है and all that. But before we get to that, I want you to take out your notebooks and draw a few structures, dot and cross or QQL structures for PCl3, H2O2, N2H4, and SO3. Try to figure out dot and cross diagram के through कि कैसे बनते होंगे ये structures. Yeah, so let's start with the first one, PCl3. Now, PCl3 comes from phosphorus, which is in group 5, and chlorine, which is in group 7. So what we need to know is that how many electrons do they need? So phosphorus needs 3 and chlorine needs 1. So obviously phosphorus goes in the center. So that's the thought process you need to have. The one that needs more goes in the center. So we take phosphorus that goes in the center, and then we have chlorine. So there is one chlorine here, one chlorine here, one chlorine here, and they each share 1 electron with this. So dot and cross, and phosphorus has 2 leftovers. There are leftovers right there, and chlorine obviously will have 3 pairs on the sides. So that's chlorine. Okay. Now, what does this show? This shows that number one, phosphorus has 3 bonds, each with 1 chlorine. So if I were to make the Louis diagram for this or QQL structure for this, that will be this one. And this also shows that the angle should be 109.5 modified. So it should be 109.5 and then 2.5 subtracted. Why? Because it is lone pair. So 109.5, you subtract 2.5, you get 107. So 107 degrees, that's what you're going to get here. That's how you get this structure. So the angle will be slightly bent, so it's better to draw it like this. If you want to draw a 3-dimensional structure for this, then that's also really simple. So put the lone pairs there. They are just occupying the whole space around it. 1 chlorine on the same plane as phosphorus, 1 chlorine outside and 1 chlorine inside. So it's important that you practice it like that. The dots and the wedges, they are supposed to show how this goes. All right, so that was pretty simple. Let's move on to H2O2. Now, again, H needs 1, oxygen needs 2. So oxygen goes in the center, but which oxygen? Turns out both of them are going to go in the center. So we'll draw oxygen here and another oxygen here and hydrogen here and another hydrogen here. So it's a pretty simple structure. So oxygen needs to share 2 electrons. So 1 here, and 1 with this hydrogen, 1 with the other hydrogen. Okay, now let's draw the electron that are outside. So this oxygen has, again, 2 lone pairs, so they go like that. This oxygen has 2 lone pairs, they go like that. And there you go. If you want to draw the structure for this in terms of lone pairs and all that proper geometry, then this could be a good structure. So draw the QQL structure for this and then make the angle. So you know that there is 2 lone pairs here, 2 lone pairs here. So the angles
bent shape hogi, sir.
Yes, bent shape hogi, exactly. So this angle should be 109.5 modified by 2 lone pairs, which means -5. So 104.5. So a better diagram would be that this oxygen goes like that here, and you have 1 hydrogen here, 1 oxygen here, and then again the lone pairs here, which give me another hydrogen like that. So there you go. That's the structure we get. Pretty simple. Moving on, N2H4. N2H4, which is also hydrazine. Hydrazine is a very useful compound when it comes to making. So I know 2 uses of it. One is used to make explosives and obviously very effective poisons, although it's a very painful thing. But a better, more useful process is that you use it to make those airbags in cars. So hydrazine breaks down in presence of sodium. So बहुत ज़्यादा gas निकलती है, nitrogen gas, और वो काफी useful होती है. So we can use this hydrazine. So hydrazine structure would be, again, nitrogen needs 3 more, hydrogen needs 1. So nitrogen goes in the center. Which nitrogen? Both of them. So there you go. Both of the nitrogen in the center. They're going to share 1 electron with each other. 1 electron with hydrogen here, 1 with another hydrogen. one with a hydrogen here, one with another hydrogen, and then lone pair on each one of them. So there's no reason that I'm drawing hydrogen ek niche ko ek upar ko. You can draw them any way you want. But just remember that once you draw the Louis diagram, then it's easy to figure out the angle. So according to the Louis diagram, the angle would be again 109.5 modified. So that is 109.5 minus 2.5 because there's one lone pair. So this becomes 107 again, just like ammonia. So the bond would something be like maybe ऐसा कर दें, थोड़ा सा bend कर देते हैं इसको. Okay, and again the shape is going to be trigonal pyramidal for every nitrogen. And last one we had was SO3. SO3 is interesting because you're getting an expanded octet here. An expanded octet means that you're not restricting yourself to having 8 electrons there, because again, octet is nothing but a basic myth we have. Or SO3 kya hoga कि you have sulfur which needs 2 and oxygen that needs 2. So how do you decide? You decide whichever is the biggest one. Sulfur is a bigger molecule atom, it will accommodate more electrons. So sulfur go in the center. So it's important to know this because they both need the same number of electrons. So sulfur goes in the center and you get sulfur, one oxygen here, one oxygen here, one oxygen here. And what sulfur trioxide has to do is it has to share 2 electrons with each of them. Why? Because oxygen needs to share 2 electrons. So the outer electrons are the ones that matter more. So this one, it's going to share 1 dot cross pair here, 1 dot 1 cross इस तरह से हो गया, फिर ये 2 pairs here, इस तरह से चलें. And let's see, sulfur had 6 electrons, all of them are bonded. Oxygen had 6 electrons, 2 of them are bonded. So oxygen has 2 lone pairs left over. So oxygen makes those, so we're left with 2 of them. Now, if you were to draw the caicule structure, that will be sulfur here, oxygen on the sides, lone pairs, obviously. And notice that I'm not caring about octet or not. I'm just making sure that the bonds are complete. And the angle, again, would be pretty simple. It is 120 because 360 divided by 3. It has 3 sigma bonds, 360 divided by 3, no lone pairs. So there you go. You can also say that it has 3 EDRs. So based on that, I can say that the bond structure will be something like this. Pretty simple. Okay, so that is how sulfur trioxide is made. That's out of the way, different structures and all that. Now I want to talk about one molecule that we discussed yesterday, aluminium trichloride. Aluminium trichloride was special because this was also something that defied the idea, the notion of having an octet and having an octet that's necessary for a complete shell and all that. What's happening here is that you're not getting any octet. So what you're getting is aluminium sharing one chlorine, one chlorine, one chlorine, and then that's it. That's it. The bonds are 120 because there's no lone pair. Sure, chlorine has lone pairs. In fact, plenty of them, 3 lone pairs for every chlorine, but aluminium doesn't. And yet it's making a bond, and it's a pretty solid white color ka compound. Now, here's what aluminium has in terms of electrons. Let's look at the last shell of aluminium. So aluminium is in period 2, group 3. So period 2 means it has 2s, it has 2p, and group 3 means it has 3 electrons. So 1, 2, and 3. So technically, aluminium shouldn't be able to make all of this. In fact, aluminium ko sirf ek bond banani chahiye because it has one p that it wants to share electron in and overlap it to make a complete orbital. Remember, I told you that bond is nothing but overlapping of orbitals to complete them and to get a symmetric cloud. And that is how they do it. And once they're done, the bond exists because that is the force of attraction between the 2 nuclei and the shared pair of electrons. So aluminium just needs one orbital that it needs to fill out, but it shouldn't be able to do this. So what it does is instead it tries to transfer one of these electrons in a way that is called hybridization. We will talk about that later again. And it moves one electron to another orbital. Now it has 3 orbitals that it can share an electron in. And these 3 orbitals are not just 2s and 2p anymore. There are 3 new hybrid orbitals. लेकिन अगेन हम उसकी बाद में बात करेंगे. So now every chlorine comes in, and one chlorine comes in, shares an electron here, the other chlorine comes in, shares an electron here, another chlorine comes in, shares an electron here. And that's it. Chlorine is happy because chlorine has 3 orbitals which have been overlapped and completely filled. But what about the fourth one? Chlorine does not have any electron to contribute for that fourth one. But bond is made by overlap of orbital. That is it. Bond isn't something else. So as long as you can do overlap of orbitals, you should be fine. So the nucleuses would hold that pair of electrons there, as long as there's an overlap that makes this. So वो कैसे होता है? What happens is that something else comes in and it gives 2 electrons that it can share. So what we looking for? We are looking for some orbital that has complete orbital, which means it has 2 electrons already, and just comes and overlaps it with aluminum. This is something we haven't seen in O levels, but technically it is possible because you're just looking for a pair of electrons overlapping for 2 orbitals. इससे क्या फर्क पड़ता है कि वो इलेक्ट्रॉन कहां से है? इलेक्ट्रॉन इज इलेक्ट्रॉन. Electron doesn't carry an ID card that, oh, I am the electron of aluminum and I'm the electron of chlorine, so I'm better than you and all that. Electron is electron. That's it. They're all identical in that regard. So that is why what happens is now that you are just looking for something with a lone pair, something that has 2 electrons that it can share with it. And what better thing to do than something aluminum chloride already is familiar with, another aluminum chloride. And that's exactly what happens. So this aluminum chloride, what it's going to do is it's going to contribute to the other one. किस तरह से? If you look over here, then this chlorine can technically donate the lone pair that it has. And that's exactly what it does. In fact, थोड़ा सा वो इसको बेहतर तरीके से करते हैं. I don't know if I can rotate this thing. So I'll just draw it again. So what happens is that this chlorine has 3 lone pairs, which we know already. So it can technically donate one of these lone pairs at least to aluminium. So what happens is that you have aluminium with a chlorine here is transit. Another of these aligns itself in a way that there's the aluminium here, and there's the chlorine here, there's the chlorine here, and another chlorine here. And they make a pact. What happens is that this chlorine, which has a lone pair, it gives that to aluminium. So we show that with an arrow. And this chlorine in response gives an electron to this aluminum. Now what happens? These chlorine atoms had 3 lone pairs, and now they have used one of those to make this. And now that's good, because instead of having aluminum trichloride, this thing has become Al2Cl6. It's a one big molecule. And we call this a dimer. And this bond is the dative bond, also called coordinate bond. So coordinate bond is different from the regular covalent bond in the way it is formed. And that is where the differences end. The only difference between a coordinate bond and a regular covalent bond that we have seen is that coordinate bond is where both the electrons come from one atom. So there is a lone pair of one atom is overlapping with the other empty orbital of the other one. What do you think will be the angle now? पहले उसका angle 120 था. अब angle क्या हो जाएगा? 109.5, because now aluminium is tetrahedral. There are 4 bonds that it has made. And because of that 109.5, what about the density? Will the density increase or will it decrease?
Sir, increase हो जाएगी.
Increase हो जाएगी density. Yes, that is true. Because the molecule is more compact. Earlier it was 120, they were far apart. And now it's 109.5, the density will decrease. And that's exactly what happens. Density will increase. The thing becomes a solid, in fact, because the molecules are coming closer and closer. So this is a dimer. Of course, if you heat it, there's a high chance that these bonds will be broken, just like any other bonds. And that is why that at high temperatures, we get a mixture of both of these. In fact, at any temperature, you will get a mixture of these. Or at high temperature, आपको एक मिलेगा और दूसरा उतना ज्यादा नहीं मिलेगा because the bonds are broken at high temperatures. Okay, so if you look at aluminum trichloride, the if you just google it ना, तो आपको दो तरह की पिक्चर्स आएंगी. एक आपको मिलेगा येलो कलर का सॉलिड और एक आपको मिलेगा व्हाइट कलर का सॉलिड. एंड द डिफरेंस इज दैट वन ऑफ देम इज अ डायमंड एंड वन ऑफ देम इज नॉट. तो आपके पास सॉरी येलो वाला इम्प्योर होगा जो आपको मिलेगा ना, वैसे व्हाइट होना चाहिए, येलो होने का मकसद नहीं कोई. So what happens is that in a solid, there's a high chance that this will be a dimer. And then if you evaporate it, there's a high chance that it will be a monomer. But of course, you will always get a mixture of these. Another compound that does it is BF3. So I'm going to give you BF3 and ask you to make a dimer of it, which will be B2F6. So go on, make a diagram of BF3 and try to figure out how it will make a dimer. I'm leaving AlCl3 out for you to use as an example.